Okay, guys, I apologize for the technical difficulties. It's a new system. So I would like to show you a few slides, basically, of motivation. So again, as I remind you that we are going to do this class as a flipped class. So you're going to do most of the hard work at home by watching the videos. So this week I will ask you to watch the first actual material on supervised learning, lecture number 2. Of course, you will see actually you can already see all the details on the course website. So today I would like to show you some examples and maybe a very high-level overview of the machinery that we are going to use for supervised learning. Then you watch the technical details yourselves, and then next week we are going to have some discussion. I would like to highlight a few things that maybe were not mentioned in the lecture and are important. For example, how to evaluate performance of classification systems, for example. What an ROC curve, precision recall, or confusion matrices are, for example. So basically how you evaluate performance of classifiers. And then I will show you also some brief introduction to our next topic. And then we are going to play this game again on a weekly basis. So today I would like to show to you a few applications. Then the common denominator will be what we will call supervised learning. Okay, so let's start with a very common application. So suppose I have a system with a camera, and you can find increasingly many systems of this kind that has an eye looking at the world around it. And I would like to recognize objects the same way we humans do very well. We actually don't really pay too much attention how the machinery works behind the scenes. It's a subconscious process. So suppose my camera sees this nice cat, and obviously I would like to translate this bunch of pixels into some higher level category, some higher level label that tells me that this is a cat. Okay, so this is a class of an object. And then I see, for example, another picture, and I would like to associate to it automatically some label that says that it's a dog. And I can build something more complicated. For example, if I see a picture with a few animals, I can give it a multi-label classification that you have both cat and dog in this picture. Okay, so this typically goes under the name of object recognition. Okay, it's a very important application. Basically, it's probably one of the hallmarks of computer vision, if you will. There is another flavor, or it is usually defined as a different problem, but basically staying within the domain of computer vision, you can also talk about the so-called object detection problem. So for example, I'm going to run through this image with a window. Okay, for example, I extract a sub picture in this red window, and I would like you to tell me whether there is a face in this window. And in this case, of course, you're going to tell me that there is no face. But then I'm going to shift this window around, and I will, for some windows, I will tell you that there is a face. Okay, so and then I can leave only the locations of these bounding boxes where I detected this object that is called a face, and you have the locations of all the faces detected in the image. Okay, so this is called object detection. Of course, I can apply it to different classes of objects. I can do it for faces, I can do it for cars, I can do it for pedestrians, for example, imagine about something like an autonomous vehicle. And actually, when you recently took a picture with your smartphone, of course, you notice that it automatically detects faces, right? For example, it focuses the camera on faces in the scene. So behind the scenes, this is what is working there, right? There is some kind of an automatic object detection algorithm. Another application that I'm giving you on purpose because it will produce a slightly different output, age prediction. Okay, so suppose I have a sequence of these images. This is my son, by the way. So you have basically, as the input, you have a face image, and you would like to predict the age. Okay, so you would like to predict the age, and the age is not a category label anymore. It's some kind of some kind of a number, right? Of course, you can quantize your ages into, let's say, into integer numbers, but theoretically, this is just a continuum of values, okay? So if we talked about object detection and classification, you can actually do it on a pixel basis. So for example, you take this scene, so you can predict for every pixel to which object it belongs, right? And give it a class label. You can say, for example, that, for example, this would be a car, and this would be a pedestrian or a bike rider, and this will be this will be the road. So you color every pixel with some class labels. Okay, so and as a result, you get both object detection, but you also get segmentation. You actually segment the car, for example, from the rest of the background in the scene. And so you also give labels, of course. So this is typically called semantic segmentation. Okay. Another problem that is very common in computer vision, you can imagine many important applications that rely on this automatic task as some kind of basic ingredient. Actually, to stay a little bit away from images and pixels, let me give you another example of an application that is also quite important. So, actually, I would like to audio working. So imagine that you have a waveform input, an audio input, and you would like to recognize the text. So just
out of the night that covers me, black as the pit from pole to pole, I thank whatever gods may be for my unconquerable soul. In the fell clutch of circumstance, I have not winced nor cried aloud. Under the bludgeonings of chance, my head is bloody, but unbowed. Beyond this place of wrath and tears looms but the horror of the shade. And yet the menace of the years finds and shall find me unafraid. It matters not how strait the gate, how charged with punishments the scroll. I am the master of my fate. I am the captain of my soul.
Well, just we had a few minutes to listen to this masterpiece of English poetry, but anyway, of course, the obvious application here is that you have as the input some audio recording of speech, in this case, speech and music, and you would like to translate it into text. So this is called speech to text or speech recognition. And of course, you can imagine that this would be the fundamental ingredient of any voice-based human-machine interface. So, for example, if you want to speak to your machine, speak to your smart home, speak to your computer, speak to your whatever device that you would like to speak to, basically it must recognize your speech, right? It can be as simple as just recognizing a certain known set of commands. But if you would like to, for example, dictate text to dictate your email while you're driving to your smartphone, then it needs to be slightly more complicated than that, right? You need to automatically detect basically unstructured sentences that they do not necessarily follow some certain rules that, for example, voice command interfaces typically impose. Or, for example, you can take a movie and you would like to produce closed captions. You would like to produce subtitles. And this is today performed automatically. For example, if you go to YouTube, for certain languages like English, for example, and Spanish, it would automatically produce closed captions, which work reasonably well, quite well, actually. There are very few mistakes. And this is another application that has no relation to vision, but again, we'll see that it will fall into the same category of supervised learning problems. Another example is machine translation. So let's take this, for example, this poem, which is written obviously in the English language, and suppose I would like to translate it into Italian. So I will take my text as the input. I will produce another piece of text that might be structured differently. Certainly it will have a different length. It will have a different number of words in this text. but we will see, we will talk about language models and specifically these applications like machine translation. We'll see that we have a tool that will work particularly well for sequences, but you will still require this machinery that is called supervised learning. But by the way, this is my translation. Another example that I would like to show you, just to emphasize that the output might be different from, for example, class labels or pieces of text that we have seen here. Suppose I take a low light image with my smartphone. So this low light image, of course, I enhanced the dynamic range in such a way that we will see something in this image, but because of the low light conditions, it suffers from a lot of noise. And you can see I have two magnified regions in this image. That you can see the noise, how it corrupts the features of the image. And I would like to give this image as an input to some automatic process that, as the result, will predict how this image could have looked like if it were taken in better lighting conditions, let's say longer exposure. Okay. So this is so basically inside, for example, your smartphone, there is a piece of hardware, an ASIC, that does some kind of automatic processing steps to images, taking the raw output of the pixels of the digital camera until what you see on the screen. And there are many manipulations that can be done. The recent trend that emerges in the imaging community or the image processing community is to do some or even all of these steps by learning. Okay? And there are many things that you cannot model by hand, or you can model better if you learn from examples as opposed to modeling them by hand. And many basic elementary image processing operations, like, for example, how do you upscale your legacy DVD content, which has 480 interlaced lines, to some 4K screen. So you need to invent information in the vast majority of the pixels, right? So you have a huge gap of resolution between that legacy standard definition content and this Ultra HD display capability that you have on a newer device. So how do you invent new information better than just doing some simple bicubic interpolation of the image? Because that would really look bad. It would not be sharp. So there are very good techniques today that allow you to do it. So essentially, what I'm trying to point out here is that the output here is an image. It's not a class label. It's not a paragraph of text. It's an image as well. But still, it will fall under the same category of supervised learning. Okay. Another example, again with audio.
The second bow falls upon the green of the first. The result is to give a bow with an abnormally wide yellow band, since red and green light, when mixed, form yellow. If the red of the second bow falls upon the green of the first, the result is to give a bow with an abnormally wide yellow band, since red and green light, when mixed, form yellow.
So what we had here, we had two examples of audios. In the first example, it was audio with some background noise, actually a realistic background noise. For example, when you talk over the phone in some noisy environment like a cafe, this is what you would typically hear. Okay, so there I think the average power of the background or the signal to noise ratio was about 5 dB, which is not terribly low, but for example, it would ruin most automatic speech to text applications because that background noise is quite strong. And what you heard afterwards, the waveform on the right, was a cleaned and enhanced signal from which you recovered the speech and suppressed all the background noise. Okay, and this is done completely automatically. Of course, it was trained before. It is a learning system. It's completely learning based, and you can do a lot more. For example, typical audio sensors today use a microphone array, a few microphones. It can be sensitive to directivity, so I can actually track the speaker, for example, in an environment like this room, and I can suppress by using digital filtering. I can suppress anything that comes from different angles. So then, of course, how to steer my beamformer, how to steer the direction into which I'm listening. This is something that can also be learned. Okay, so basically you can have more, very much more complicated settings in which you also have some active sensing components to the system. Okay, so if we have time, we'll speak about these kinds of. This would correspond to some kind of an attention mechanism that is one of the probably one of the strongest techniques that exist today. So let me put it in some perspective. So we have seen a few applications. What was common to these applications is that we had some input data on one hand. For example, we had images, or we had text, we had audio inputs in the examples that I showed you. I'm just showing you examples with images here. And as the output, we wanted to produce something, so to produce something that we can think of it as a label. Let's call the input as X and the output as Y. In the case of object classification, for example, the label would be one of the visual categories that we would like to classify our object to. For example, 1,000 different categories. One of them is cat. So I will be outputting cat for the input of this cat photograph. The other case that I showed to you was object detection. And in object detection, I will present you with a window with some visual content, and you will tell me whether there is a face or no. So it will be a binary label, true or false. Okay. In the case of age prediction, I would like to produce a number, some continuous number corresponding to the human age, let's say in years, something like that. And then in the image enhancement example, or in the audio enhancement example, the input would be some noisy signal, the output would be some cleaned signal or enhanced signal, maybe in a different resolution. For example, if I want to upscale my image to a bigger display, to a higher resolution display, then the number of pixels here might be different. Okay, but the output is an image. Okay, and typically of course, our goal will be to estimate Y from X. So I'm giving you X, tell me what Y is. Okay, and typically we'll distinguish between regression task and classification tasks. In regression, Y is continuous, can be vector valued, like in the case of this image. And in classification, typically Y will be discrete. Okay, I'm trying to convince you that it's exactly the same problem, but it just has different names in two distinct settings. But it's exactly the same problem. Okay. So in order to tackle this problem mathematically, we'll need some elementary notions in probability. Okay, so let's think of some much easier problem. Easier because I need to draw it on a two-dimensional screen. So let's think of a much easier problem. Let's say our data, our input, will be, let's say, the age of a person, and our Y label, it will be a regression problem. It will be a continuous label axis. It will be the weight. Okay, so age versus weight. And I would like to predict your weight according to your age. Okay, it's a reasonable problem. For example, if you have children, you typically see these growth curves, right? There is some probability distribution that you can take from the entire population, right? So you have age on the horizontal axis, weight on the vertical axis, and you have some distribution like this. So what is drawn here are the level lines, equiprobable lines of this probability density function. Okay, and in the language of probability, of course, this is called the joint distribution of X and Y. Okay, so X is a scalar, it's a random variable, Y is another random variable, and X and Y is a two-dimensional random vector, and this is its probability density function. Okay. Now we can talk about marginal distribution. What is a marginal distribution? So the marginal distribution, let me try to give you a physical example first. So imagine that what I'm showing here is some physical density of a material. Let's take an optical example as our mental picture of this. So suppose I have some transparent object, a cube of glass, and within there is some density of light absorbing material. Okay, and now I will shine light through this object, and I will see a shadow of that material on a screen, right? So the more light is absorbed, the darker is the shadow on the screen, right? So essentially, I will integrate, let's say I will project the light, I will shine the light vertically through this object. And what I will see a shadow here. So it's just flipped, of course, but basically this means that I have a very dark shadow because there has been a lot of material that absorbed my light. Okay, so I will essentially integrate through this joint distribution in one direction, in this case in the direction of the axis y, and as the result I will have another function that is now a function of a single variable, function of x. This is called the marginal distribution. Okay, and this process of integrating over some of the coordinates is called the marginalization of the distribution. In this case, I integrate by the second argument and I marginalize it and get a distribution with respect to the first argument. So this will be the marginal data distribution. This is how the essentially it tells you how the ages in the population are distributed. So it is a bell-curved. It's a bell curve, right? Bell-shaped curve. I have some amount of very young children. I have a small amount of very old people, and some peak in between. Okay. I can do the same in the other direction with respect to the first coordinate, and then I will get the marginal label distribution. So in this case, the label is the weight. So this is the, I will find people about this weight most abundant in the population, right? So I will probably find very little people that weigh 2 kilos, and I will find very few people who weight 200 kilos. And I will find, I don't know, 70 kilos in this peak, something like that. Okay, so these are the marginal distributions. I can also talk about conditional distribution. Okay, what is a conditional distribution? As opposed to integrating with respect to one of the coordinates, I can just take a slice through this two-dimensional function. So I'm giving you x. Okay, I'm giving you x. I'm telling you that this guy is, let's say, 20 years old. Can you now tell me how his weight is going to be distributed? You just fix the x at 20. You slice through this two-dimensional function. What you are going to get is something. That something will require renormalization, right? Because it will not necessarily sum to 1. After I renormalize it, I get another probability distribution, and this is called the conditional distribution. In this case, when I'm conditioning on x, I'm getting the conditional label distribution of y, the label, given x, the data. Okay. Now, why do I care about conditional distributions? Why is this a useful tool? Because as we certainly all know, this allows me to solve estimation problems. Okay. So suppose I have this marginal label distribution. It is called the prior distribution. So, for example, I'm asking you to tell me the weight of a person. You haven't shown me the person yet. I can already tell you how the weights are going to be distributed, right? This is my prior knowledge, my a priori knowledge. Before making any observation, before making any measurement, this is how the weights are distributed in the population, right? This is the marginal distribution of the labels, right? This is what I know about the population. And maybe in one country it will be one type of a distribution, in another country it will be slightly different, but this is what I know a priori about the population, okay? And then I will observe the data. Now, you told me that this person is 20 years old, so I observed the age, okay? So now you have a measurement, you have an observation. And from this measurement, you would like to go to the posterior distribution. This is the conditional distribution, conditioned on the data, on the measurement. So now you have some additional information. And as the result, you get the posterior distribution, which is the conditional distribution, conditioned on the data. Now, what can you tell me about the statistics of this curve and this curve? Specifically, second order statistics, the variance. So as you can see that I had some quite big variance here in the prior, and once I observed something, I have a lower variance. So what does it mean in simple terms? It means that I'm more certain about my result, so I can give you a better estimate with a more narrow variance once I observe the data. If this variance didn't decrease, my measurement is useless. Doesn't contain a lot of information about the quantity I'm trying to estimate, right? If the distribution didn't change after doing the measurement, we will say that X and Y are statistically independent, right? This is what statistical independence means. Okay, so again, we'll use these tools in probability all the time. It will be one of our basic mathematical tools. So I prepared a short write-up, some kind of a survival guide to probability and statistics. I refer to this as it's a summary of well-known things for those who don't know them well. Okay, so of course they are well-known, but sometimes might be unaware of this or that notion or this or that result. So I invite you to even briefly go through it and just make sure that you have at least you know all the terminology and you know what I'm going to talk about, because I'm going to use these tools in the first set of video lectures, and of course as we proceed with the class we'll continue using these tools. So again, please have a look, and you can actually do it in real time as you go through the video. If you encounter something that is not clear, you can have a look at this reference. Okay. So again, back to our estimation problem. So what we are going to do, the approach that we are going to take to this learning problem, we are going to build a parametric model. Sometimes it is called as a hypothesis for this conditional distribution. So I have this conditional distribution because basically this is what my estimator will output. It will output the distribution of the label conditioned on the data. Okay. Of course, if you insist on getting one number, I can give you the mode of this distribution, this peak, okay, or the mean or whatever, right? But in this process, you actually get the posterior distribution for free. You also know, for example, how certain I am about my answer, right? So this is a very valuable piece of information. But basically, this distribution can be a completely crazy thing, and it typically is a completely crazy thing because, for example, your input image is some hugely dimensional signal. You output, for example, some distribution over visual categories, let's say 1,000 visual categories. The input space is crazy. This conditioning of the data is crazy. Or, for example, when you work with regression, your output is again this hugely dimensional image. And how exactly do you model this distribution, right? You need this conditional distribution of the data. So what we are going to introduce, we are going to introduce a parametric model for this conditional distribution, for the posterior, okay? For the label given the data. And our tool that we are going to use for our purposes in this course will be a neural network. So we'll see that a neural network will be just a fairly rich family of parametric functions that take something in the input and map it to something in the output. And you can tune how this map works by a finite dimensional set of parameters that I'm denoting here collectively as theta. So all these weights and biases in the layers of a neural network, these are all dimensions of this parameter vector theta. Okay, so you have a parametric function, can be a crazily complicated one, that hopefully can model, maybe to some modeling, up to some modeling error, can model the real thing, the real conditional distribution that is your objective to model. Okay. And now the estimation problem simply boils down to finding this optimal set of parameters that will minimize the distance between the real conditional distribution and the one that we model. So imagine that you have two curves and they don't match perfectly. So I have one ground truth curve. This is py given x, okay? And then I'm allowing you to twist the other curve by tuning the parameters theta until the two match perfectly or match in the best possible way. Because it might be that the space of these parametric functions cannot reproduce precisely the shape of this distribution Py given x. Okay. So then we would like to minimize some discrepancy, some distance between these two distributions, minimize them over theta. Okay. And this is how we can formulate any estimation problem in general. Okay. And what we are going to use as this distance, or at least this is a typical choice. Of course, we can put in many more different choices. It's called the Kullback-Leibler divergence. It's not exactly a distance because it's not symmetric, but essentially it boils down to the expectation with respect to Py given x of the negative logarithm of this model distribution P hat theta y given x. Okay. So this, if you plug in this distance into the minimization problem over theta, you're going to get a form of an estimator. Okay, and of course, the sought quantity would be the parameters theta. Once you found this quantity, then you use this theta to model your distribution. So you plug into it your new observation x, and it will give you the distribution of y. And then you can, for example, take the peak of the distribution, the maximum of the distribution. Okay. And again, as I said, you can, instead of writing this basically by simple rules of probability, basically what is written here can be written simply as the expectation of P xy, the joint distribution, or maybe in simpler notation, again, this is just an expectation over Pxy of the negative log of P theta y given x. Okay? And again, if you don't remember what an expectation is, then go to that reference. I have a precise definition. Okay, and obviously our goal is to bring this to minimum over theta. Theta is our degree of freedom. This is what we control. These are the knobs that we can control. Okay. So are we done? Looks like we are done. So I will solve this problem, and you get the best estimator in the world. What is the problem with this? We don't know Pxy, right? If we knew Pxy, then basically we don't need to bother in the first place, right? We don't know Pxy. It is completely unreasonable to assume that we know Pxy, this joint distribution of the data and the label, right? Because this is everything we could possibly know about our data, but obviously we don't know it in any reasonable situation. So we would like to estimate this expectation with respect to a probability density that we don't know. Okay, what can we do? And here basically we transition from the domain of probability, from theory of probability, to the domain that is called statistics, right? So if we don't know to model something as an analytic function, let's take a finite sample and try to model it from a finite sample. And this finite sample in our setting is called a training set. So in the training set, we'll sample independently from, and again, I will emphasize all the assumptions that are typically wrong that we are going to make in order to at least be able to prove something. We will sample pairs of points, pairs of data and their labels, corresponding labels. So xi, yi. This is the finite sample with capital N points from this unknown distribution Pxy. Okay, this is called the training set. So these are representative examples that I sampled from my data distribution or data and label distribution, and now I will estimate my expectation using this finite sum. So this is the average, and this average by the law of large numbers, as you can remember, it's a good estimate for the expectation if n is big. Okay. So this is going to be my estimate, and now instead of minimizing, I would like to minimize this quantity, which is called the out of sample loss, and this quantity is not computable because I don't have access to this distribution. Instead, we'll only be able to manage this, what is called the empirical loss or the in-sample loss, which is tractable because I'm computing it on a finite sample. and I'm going to minimize it over theta. Okay, so this is a solvable problem. It might be very complicated to solve. We still don't know how to. When I write arg minimum of something, we still don't know how exactly we are going to find that arg minimum. But at least we have a function of some vector valued argument. Theoretically, it has a global minimum, or it might have multiple global minima. But then we'll be satisfied with one of them. Okay, it will be a very complicated problem actually to find, or an unsolvable problem to find that global minimum. We will be typically satisfied with a local minimum, and then there is some magic that tells us that still these minima are usable. Okay, but we're going to talk about this when we talk about optimization algorithms. Okay, but for now, let's say that we have some magic black box that you give it a function, it returns you the arg minimum, the minimizer. Still, we have a different function. We are approximating our ideal out of sample loss, our ideal expectation, by some finite sample average. Okay, and then of course the problem that, or the question, the natural question that you might be asking yourselves, why will it work? Why, when we find parameters that minimize this empirical loss, this in-sample loss, why then, given a new previously unseen instance of data, why is it going to generalize? Why is it going to produce anything useful? And this is a very important question in learning. It is called generalization. So we found this theta star that minimizes the in-sample loss. Is it going to minimize the out-of-sample loss as well? If not, how big will be the gap? And how can we guarantee that this gap will be reasonably small in order for us to be able to use this solution at all? Okay, so basically all this is the baseline for what is called supervised learning. Supervised because we are providing for each data point some, basically we are taking examples of data points with corresponding labels. So in this way we supervise our machine. We are essentially building an interpolator in that huge space of joint distributions. Yes? So just to so the question was whether, if I understand it correctly, so the question was whether this quantity that is written here, this in-sample loss, is whether it is a random variable itself, right? Because I can sample in multiple ways. So again, imagine that I sample at random, let's say IID, I sample at random, from PXY, I sample a finite set of n, capital N points, okay, or pairs, X and Y, right? And then I evaluated this loss function, this in-sample loss. I got some number, right? It's a scalar. No, not every point has the same probability, because some points, so imagine that I have a probability like a probability distribution. Let's go back to this visualization. I have a probability distribution. I will have many points coming from this region, and I will have no points coming from this region, right? So basically the density of my sample, if I sample enough points, you will see the density of what is depicted here. Of course, it is much more complicated to reach any reasonable density estimation in a very high dimensional space, but that's a challenge. So again, what you are saying is that you wanted to see some weighting of in this, basically in this sum, you want to see some weight. Well, the way I sample, it's not a uniform sampling from R2 in this case, right? It's not uniform sampling. I'm sampling it from the density, from the original unknown joint density. So suppose this joint density has a very narrow region where the density is concentrated. I will have most of the samples coming from that region, right? So this weighting that you are looking for is already in the construction of my training set. Okay. Of course, there will be some variance. What I was trying to say is that this quantity itself is not a deterministic quantity; it's a random variable. Take another sample, another sample with n points from the same distribution, you will get a different number here, and that number has some variance. When you make n big, this variance will go to 0 when you have IID sampling, right? This is what is called the law of large numbers. Okay, it will converge to the mean, and actually, what happens to the distribution as it converges to the mean is something that allows us to make statements about generalization capabilities. Okay, again, I'm not going to go deep into this theory in the video lecture, but at least some flavor of how it should be done. The problem is that the existing theory, like for example the notion of VC dimension or Rademacher complexity, theoretical tools that have been used to prove generalization bounds for many machine learning models, are practically useless for deep neural networks that have the bounds that you get are very loose. So that's why, because I think it's not very practical, I'm not going to steal your time on showing you all this theory. Okay, yeah. About the Gaussian mean width. Okay, so Gaussian mean width. Let's. I promise I will speak a little bit about it, but first we need a few notions, at least how a neural network works, and basically what are the building blocks, and then I will show you some results that rely on these two. Okay. So the format I suggest, we still haven't seen anything detailed yet, so I don't have much to discuss. So then next week we are going to meet. Again. I will wrap up what we have seen on the video lecture. We'll discuss some topics that I find interesting. If you have other topics that you find interesting, please bring them. We'll have a discussion. I would like to make it as interactive as possible. I will prepare some slides. Probably I'm going to record them just to make sure that you can go back and watch the video. And then I will show you another kind of introductory slides, maybe a little bit less, about our next topic. Okay, and then again we'll repeat this task. We are going to have an assignment to watch an hour and a half of video or something like that during this week. Hopefully I motivated you enough to understand why we are going to go into all those mathematical details, basically why supervised learning is important. Of course, we will shift gears and we'll talk about more interesting and more complicated training regimes, which do not rely on this sample-wise supervision. But this is probably the easiest one to talk about, and it's also very powerful. Deep learning, when n is big enough, deep learning works superbly well for supervised tasks. Okay, but we'll see that there are other tasks that do not require massive supervision, and there deep learning excels as well.